Hello, everyone. Welcome back. Let's talk about some other matters that I think you'll find of interest. The dot product and the cross product is that about which we will speak in this discussion. So we'll see how it all plays out. There are many things that can be said about the dot product and the cross product, and there are numerous ways to look at these two fascinating products that are used in engineering and physics. So the dot product and the cross product are what we're going to be looking at. And at the end of this discussion, there are going to be three documents, so to speak, that'll essentially scroll all as one, that'll talk about this in perhaps more detail for you. Those who have me as a teacher this particular semester in which I'm talking right now, can also see this on Canvas. If you can't see this on Canvas, I do have it. It'll be accessible to you within this video. The first of the documents will be, I'm not sure how good it can be looked at, I guess. The first of the documents that you'll be able to see at the end of all this is a look at the dot product. After that, there's a document called the cross product. And the third one is more on dot product and cross product. So they'll all be accessible to you when we get there at the end of everything here, guys. So let's see what we can say today, and perhaps we have to extend it a little bit further and we merge some videos. But what is this all about, you guys? What are they talking about? Well, regarding the first document, a look at the dot product. We can find the dot product for any two vectors in any n-dimensional Euclidean space. But the n-dimensional Euclidean space, which concerns us for our purposes, is three-dimensional space. Three-dimensional space is what we live in, so it's good to be able to look at it within three-dimensional space. And there's a number of ways this can be written. Like I said, there's even the way we write it, the notation that we choose to use should be chosen, I guess you could say, carefully, but at the same time, there's a lot of ways we can look at this. We will consider three-dimensional space with two vectors, A vector and B vector, both with origins at 0, 0, 0. So you've got A vector in three-dimensional space, and the way it is written, and like I said, we can play it like this, but we just as easily could write it in different ways. Let me show you, and then we'll kind of we'll play the game as we feel we need to play it, I guess you could say. A1 I hat plus A2 J hat plus A3 K hat. Those are the unit vectors along x-axis, y-axis, and z-axis respectively, namely I hat, J hat, and K hat. And then the A sub 1, A sub 2, A sub 3 are scalars by which you're multiplying these unit vectors. Like I said, I hat's associated with the x direction, J hat is associated with the y direction, and K hat's associated with the z direction. A lot of ways this gets written, guys, and I'll just try to get some of the formalities out of the way here. They both have origins at the origin. The origin in three-dimensional space is 0, 0, 0. Frequently, you'll see it written. If this is the way I'm saying it, you see the vector written like this. Depending where you look in the literature, I think, you can write it like this, and this is kind of giving you an idea. There's other ways to write it, I think, as well, but you frequently see it written like this for the vector. And for B hat, and for B vector rather, we have B1, I guess A associated with locase A, B associated with locase B. We got this, and that, of course, just following the logic that we're presenting, we can say write it like that. You just as easily, I don't want to, beat this thing up too badly, guys, but what we're saying here, when you want to look at something like this, we can essentially say when we're writing this, like I said, you could write it you got this guy looking like this and the other guy looking like this. Same kind of argument here. I mean, you got this right here and you got this right there. So they're both associated with one another, I guess you could say. There's another notation that's maybe more intuitive. I think there is. Doesn't really matter, guys, as long as we got this thing under control and we can actually do something about it. You could have just as easily, I didn't approach this particular discussion with any other notation, at least right now, immediately. I started here, and that's kind of where we're going. That's kind of where we're staying. Like I said, we got this right here, which is the same as that, and we got this right here, which is the same as that. Okay, I mean, you could have said, and you're going to see it later on, so it's not going to shock us too badly, you could have done A vector equals the lowercase a sub 1 could have been written a sub x I hat. And I'll be using that later on for some of the discussion. The lowercase a sub 2 could have been a sub y written like this. And the lowercase a sub 3 could have been a sub z written like this. It's a little more intuitive. B vector would be b sub x I hat, b sub y j hat, b sub z k hat. You could write it like that. To me, that's a lot more intuitive. Since I started the discussion like this, this is essentially how we're going to go, at least for now, for some of what we have to say here. But it's as the proverbial statement goes, it's a horse apiece. Just make sure you know what you're doing here. It is clear that these two vectors are coplanar in three-dimensional space. Yeah, there's an endpoint, there's a beginning point to the vector and an end point to the vector. The beginning point of the vector is the origin, 0, 0, 0. And there's an endpoint for one vector, an endpoint for the other, so there's really 3 points that are kind of determining everything. Well, we know that 3 points determine a plane. So it's clear that these two vectors are coplanar in three-dimensional space. We also know that the tips of the vectors A vector and B vector are located at where we had said. In other words, the tips of the vectors, you guys, would be located at, for the A vector in three-dimensional space, they're located here. For the B vector, they're located here. Okay? And like I said, you could just easily have put a sub x, a sub y, a sub z right here, and you just easily could have put b sub x, b sub y, b sub z right there. Same thing. All right. We will recall that by definition, they say a couple things here. We know that a vector dot b vector, by definition, is the magnitude. Now, there's a lot of ways you can write this. So let's kind of go there initially, at least. There's there's a lot of notation out there, guys, and it's not that some's better than the other. It's just that there's a lot of notation out there. So kind of be familiar as best you can when you're dealing with this stuff, in case you encounter different things in different literature, how you say stuff. A vector dot b vector is the magnitude. It's a scalar. Is the magnitude of a vector times the magnitude of b vector. When you're done with that, and a lot of times they put, I didn't even put a dot there because I don't want to confuse it with the dot product itself. So that's true. So magnitude of a vector times the magnitude of b vector times the cosine theta between them. And that'll give you a vector dot b vector. Frequently, to make things easy, I mean, writing each one of these symbols, the symbolism right here, is its own kind of chaos, I guess you could say. Basically, the magnitude of a vector, oftentimes they just write it without putting the arrow on top. That's the magnitude of a vector. That is the magnitude of a vector. This is the magnitude of b vector times cosine theta. It's a lot easier to look at. Basically, magnitude of a vector is this, magnitude of b vector is that, and this is a whole lot easier to look at, you guys. So you get to here. Well, that's the definition, plain and simple. Why they do that? Because there are a lot of things that go on related to the dot product that are useful in engineering and physics. So there's some relevance there, and sometimes it's not easy to find an angle, so you got to look at different ways that you can actually evaluate this fascinating quantity called the dot product. Let's have a look here. I mean, to kind of go about this. Now let us consider something that will not only be of use in looking at the dot product of two vectors, but will be useful for looking at the magnitude of their cross product as well when we get to the cross product, guys. Let us consider the magnitude of the projection of a vector in the direction of b vector. Again, let us consider the magnitude of the projection of a vector in the direction of b vector. This magnitude is going to be the magnitude of a vector times the cosine of theta. So now we got to be a little careful. So we look at this, and we see what we have here. I always seem to forget you guys got the reverse feature on this thing, so I can erase a whole lot a little more quickly sometimes. So we're looking at something like this, guys. We know all this. So this is in the back of our mind. Can we make it work? So let's see what we do have. See what we can say here, guys. I'll eventually erase. A little bit more here. Okay. What is happening here? Well, we could say that, again, we can figure out, we can find the projection, and let me just kind of pick and choose here how I want to go. You're going to have access to all of this, but let me try to see what I can do. Let's find, this is a very strange thing in its own right. I mean, let's kind of come back to it. I mean, when we said that the dot product was a vector dot b vector, and that's magnitude of a times magnitude of b times the cosine of theta. Well, it's kind of neat. You could write this as a cosine theta times b, or you could write it as a b cosine theta. In other words, I could be talking about the projection of b vector onto a multiplied with a, or I could be talking about the projection of a vector onto b multiplied with b. See, when you draw, again, we're asking the question here. Let's consider the magnitude of the projection a cosine. They wanted to go with cosine, so let's go with they wanted to go with the a vector and its projection and everything else. If that's the case, this is all true, why don't you stay here for now? If you're going to stay there, guys, what's going on here? What's the significance? Well, I mean, the significance is quite striking, I guess you could say, at some level. A vector dot B vector is this, is that. It's any one of these three. That's A vector dot B vector. If I find A cosine theta and multiply it with B, I have the dot product. The dot product is a scalar quantity. Later on, we're going to talk about the cross product, and the cross product is a vector quantity. The cross product of two vectors is yet another vector that's perpendicular to both the vectors that were originally present, that were originally being cross product together. You get a resultant of that cross product of the two vectors that is going to be perpendicular to those two vectors with a magnitude of the product of the two magnitudes of the vectors times the sine of theta. And it'll project perpendicular to both of those in a right-handed fashion. That's its own discussion. Well, I just said it now. We'll talk about it later in quite a bit of detail. But right now we got this. What does this mean? Well, could say a whole bunch of things. I mean, we could find out what's happening here by saying the following. You could say, in fact, the perpendicular distance from the end of A vector to the line in the direction of B vector, or better said, to the line whose parametric equations are determined by B vector, are as follows. It's sort of doing this a little bit backwards, guys. Let's see what we can do here. Let me put a goalpost right here, because I don't think I can go beyond that and get filmed too well. So let's see. Let's stay there. What they're trying to say is there is a vector in three-dimensional space determined by B vector that is given by B vector times T, where T, now you've seen me talk about parameters earlier when I was talking about we're talking about Taylor's formula, right? But B vector times T will say, okay, let's say this is B vector, the way it originally looks in three-dimensional space, and if you multiply it by T, it goes this way, it gets bigger, B vector times T can get bigger going this way, it can get smaller too, and if you multiply by a negative number, it can go this way. So the line goes to infinity in three-dimensional space if T is between negative infinity and positive infinity. If T is between negative infinity and positive infinity. Well, what's going on here? Well, that means that basically you would have B1. We're just talking about B vector right now, and then eventually I'm going to talk about the projection of A vector onto B vector, or the projection of A vector onto a line that is determined by B vector. Well, this is the line determined by B vector. It can be written like this. So it can be written like that, which is the same as just saying the x component is doing this, and it can be going any direction now, right? I shouldn't even, should have maybe kept the dots here, the broken line, I guess you could say. When we're doing something like that, you guys, so you're looking something like this, this, etc. And that, so it's everywhere in three-dimensional space. What we got here is B sub 2 times T, B sub 3 times T, so we have this, where T is an element of the real numbers. T can be any, I said it could be anywhere from negative infinity to positive infinity. Yeah, that's called, it can be any real number, is what it is. T is an element of the real numbers. Okay, great. So we said that. What's going on here? Well, this perpendicular distance is easily seen to be when we see. What I want to do is I need to, if I'm going to find the projection of, if I'm going to find the magnitude of the projection of A vector onto B vector, I got to find how big A cosine theta is, because A cosine theta is the magnitude of the projection onto B vector. Or if B vector happens to be small, it's on the line, it's on this line somewhere that's determined by B vector. Okay, well let me draw this a little bit differently. Just to kind of, so you'll see what I'm talking, hopefully this makes a little bit of sense. If you were going to say that, okay, this guy's B vector. And we said, when you determine the line for it, well, we said a lot of stuff. I don't know how I just drew that, but I think you guys know what I'm talking about. It's not a good drawing, but make it a little bit better, I hope. Perhaps it was adequate as is. And that's B vector, and let's say it's just doing, again, guys, no ruler here, and I don't think anybody's going to accuse me of being an artist anytime soon. This right here, you guys, is B1T, B2T, B3T. Yeah, it's a line that goes infinitely long. Let me just see how that comes up on film, you guys. You should be okay, I think. Yeah, it looks okay. Looks okay. Let's stay with the white chalk a little bit too. B1T, B2T, so forgive me, guys. I just want to make sure there's some legibility here. We got this. Okay, yeah, looking okay. Okay, so you're looking at this B1T, B2T, B3T. And you've got this guy, which is B vector. And, okay, so what? Somebody could say, well, okay, I'll tell you what I'm going to do. Let me take A vector. This is the angle theta between the two. This is A vector. This is the perpendicular distance straight down. So if this is A vector, the magnitude of A vector times the sine of theta is this distance right here. True. This distance right here would be A cosine theta. Okay, that length right here is A cosine theta. That makes sense because if you square the length of this leg, which is the square of the length given by A cosine theta, and if you square the length of this leg, which is given by the square of the length given by a sine theta. Look, in plain English, if you square this quantity and square this quantity and add the two together, you get a squared. A squared cosine squared plus a squared sine squared is just going to be, take the a squared out. It's, at the end of the day, a lot going on here. If you square this stuff, basically what I'm saying is if you took a cosine theta, squared it, took a sine theta, squared it, that equals, the proposition here is it equals this. Is that true? Yeah, I think it is. We got a squared cosine squared theta plus a squared sine squared sine squared theta. You take the a squared out of it, just old-fashioned mathematics, guys. Cosine squared plus sine squared is 1. 1 times, it's a squared times 1. So on and so forth. Well, it's good to use that trigonometry. It's good to use that trigonometry and get an idea of what we're talking about. So we wrote some of the stuff that we wrote right here, you guys. See exactly here, guys. Since I'm going to have the documentation is already available to you fully if you're in the courses I'm teaching. Otherwise, it's going to be the video anyway. If this for this to be available for as long as the video itself is available, we're going to have all this documentation available to you. So, with that in mind, we don't have to do everything that's here because the document's going to be available to you as well. We looked at this. Keep tinkering with it. So, okay, where do I want to go with this? Well, I said a bunch of stuff here. I'm trying to get, I guess in a very backhanded way, you guys, I'm trying to get out of the woods and say, this is great. There's nothing wrong with it. Of course there's nothing wrong with this. This is a definition. Of course it's great. Of course it's going to work. And it's very good for us. We know it's true. What if you just don't know in three-dimensional space what that angle is? If the angle's not available to you, are there ways you can do mathematics to still find this very useful dot product, which is defined to be this? But if I can't find certain things, are there other ways I can get around it and still have that same answer? That same answer defining the dot product to be AB cosine theta. There are ways to do it. Well, like I said, there's different things out there, you guys. The big thing here is I'll read it out and we'll kind of make the moves as we need to make the moves, I guess you could say. To simplify the notation, additionally, clearly we can see that of all possible distances from the end of a vector to the line b1t, b2t, b3t, the perpendicular distance is the smallest distance possible. It is the minimum distance between the point and the line. As shown earlier, the magnitude of the projection of a vector in the direction of b, where the endpoint of a vector from where the minimum perpendicular distance from a1, a2, a3 to the line b1t, b2t, b3t is going to be measured is going to be this. So what are we saying? What we're saying here in plain English is the following, guys. What they're trying to say is, okay, we talked about, we said, hey man, let's get a proposition here of can we get a vector and b vector, can we somehow get the projection, the shadow, so to speak, of a vector onto b vector? Can we talk about it? Or the shadow of b vector onto a vector, the projection of b vector onto a vector. Can we talk about it? Can we, again, draw some conclusions? What I was saying there, I'm not sure how, it's always easier when you're looking at this stuff live, I guess you could say. Okay, we simply just took this guy and took a different look. We took a different look at this guy and kind of looked at it from this way, so it looks like he's going like this. The projection of A vector onto B vector is right down here. I don't want to draw more on this thing because I don't know. I'm not incredibly comfortable with it because it might look a little different. But you could kind of say that I could make A vector into the sum, the vector sum. I could make A vector into the vector sum of the projection of A vector down here onto B vector plus the vector that has the minimum distance from the line defined by B vector up to the endpoint of A vector. Basically, I don't want to write this guy. I don't want to do this unless I do it and then erase it or something. But I can make a vector here and a vector here added together and I get A vector. I don't want to do that. The fact that I'm erasing this like that, I don't know, there's a little bit of a smudge on there, but okay, you know where I'm coming from, guys. Essentially, guys, we can find the minimum distance from the endpoint of the vector, right here, to the line defined by B vector, given by this whole song and dance. That minimum distance is perpendicular. It's a right triangle. Well, in a backhanded way, that's why this was justified anyway to begin with, when I was doing this stuff. Well, let's use that same reality, you guys, to try to figure out what we're doing. So there's a lot happening here. There's a lot you can say here. There is, I guess you could say, and I don't, like I said, there's more. There's this point right here is 0, 0. 0, 0, 0, actually. That's what this point is. This point is, and again, I hate writing this stuff because I think it just there's too much there. But you know the end point is B1, B2, B3. It's the very end of that whole thing. The end point of this guy right here is A1, A2, A3. And this guy right here is B1, B2, B3, and I'm not even going to put an arrow there for you know where it's going. This right here pertains. All this right here pertains to this. Okay. So that's it. So what are you going to say about it? What are we going to say about this whole thing? We're trying to find, I tell you what, let's see if we can, everything we want is contained in a right triangle if we can find a right triangle. The projection of A vector in the direction of the line defined by B vector, say it again, the magnitude of the projection, I guess you could say, the magnitude of the projection of A vector in the direction of the line or onto the line defined by B vector is associated with right triangles going on. There's a perpendicular distance from the endpoint of A vector dropping down to the endpoint, dropping down to the line defined by B vector. It doesn't have to hit B vector. B vector might be really small. It might be really big. The perpendicular hits somewhere on the line defined by B vector. This is a right triangle. This reality has to take place if you're trying to find the minimum distance from A1, A2, A3 to the line defined by B vector. It's not necessarily B1, B2, B3, but it's the line defined by it. I got to find that minimum distance. When I find that minimum distance, I know how big this is, and I also know how big this is by using the Pythagorean Theorem, and then I'm getting the projection A cosine theta, and that's here. I want A cosine theta because A cosine theta times B is AB cosine theta is another way of saying the dot product A vector dot B vector. Now people are saying, what are you talking about? What's the big deal? You just wrote it down. This is true. Yes, it's true. But is there another way to express it if I am missing something? Or if I want to find something out? The more that you know, the more chances you have to solve something if you can take different paths to get to where you need to go if your path is blocked one way. It's the big thing. It's a big thing in mathematics, in physics, in science. Okay? So, if that's the case, you know, in terms of parametric equations, let me try to kind of argue this, I guess, in different ways here, guys. I don't want to, there's things I want to erase, there's things I don't want to erase, I guess. So I got to be careful which one I'm doing, what, you know, what I'm erasing and what I'm not erasing. Let's have a look. All right, we know a lot of stuff. You can always come back to things. Almost want to leave that there. Eventually, a lot of the stuff's going to have to go, but we'll see when we cross that path and what we do. We know what it is. We know what we got to do. For this distance, the A cosine theta that we're talking about, in terms of the parametric equations of the line in the direction of B, we have the following. Guys, I want to make a point here. I don't know what's going on here. There is some value of t that'll bring it there. What that value of t is, I don't know, but if I do the mathematics right, it should be on the mark. What are we trying to say here, guys? What we're basically saying is, I guess I can sort of make this vector expand or contract if it's a very long vector, or if it's going the other direction, I have to multiply by a negative number, whatever. But I guess I could take this vector, I got to take this vector, and I've got to make it, in this case, I got to make the vector expand. How do you make B1, B2, B3 expand? Why don't you multiply that vector by the scalar t, and it gets bigger. You multiply by the scalar t, you got B1t, B2t, B3t, and it becomes as long as that. Look, in plain English, I guess you could say this. You could make it... Now, you got to be careful how long that thing is, right? I mean, what we're saying, you could say, you would basically take, and you would take B1t, B2t, B3t, yeah, I said generally it goes like that, but let me say t is some specific number that gives it that length. What are we talking about? I'm talking about take B1t, that length, that x component, it's an x component, square it. Take B2t, that y component, square it. Take B3t, take that, so take the x component that you arrive at. Remember now, this isn't, I put it on a blackboard, I get it, but this is in three-dimensional space. I can put it on a blackboard because the two vectors are coplanar. There's no lie here, I guess you could say. There's nothing deceptive in this. These are vectors in two vectors in three-dimensional space with a common origin, and wherever they are, I can pretty much put them in one plane. The plane I'm putting them in is called the blackboard. That's fine. And they're here. And I can make this guy, you know, I can deal with that vector and make it anywhere as big as I want on the line determined by B vector. Well, I'm going to say t something specific right now, guys. B1t is the new x component. I'll square it. B2t is the new y component. I'll square it. B3t is the new z component. I'll square it. Yeah, I'll add them all together. This is just the Pythagorean theorem in 3 dimensions, ladies and gentlemen. You get to here, and that's A cosine theta. Yeah, true. These are all squared, each one. Yeah, take the t squared out of there, please. Yeah, it's a true story. Wait a minute, what's this b1, b2, b3? Now we're back to what? Now we're back to the size of the original vector. And when you square each of the components of the original vector, you're talking about the size of the original vector, b squared. And when you square root it, you just got the original vector, b, in terms of size, in terms of the magnitude. What are we talking about? Well, let's talk. Let's talk. The square root of a product is the product of the square roots. Okay. Number of conclusions you could draw here, to tell the truth. But let's talk. Let's see what we got. There's a number of ways you can go here. Again, there could be a negative, there could be a positive. I think we're trying to get around some stuff here. The fact that the magnitude of a vector, so let's see here, we're just talking about magnitudes here when we're talking about this. This should not be an issue, though it could be, as far as how this stuff looks. Let me write to you. Let me not try to split too many hairs on this. I think it's more important to just actually get this thing right. Let's kind of look at a bigger picture of this if we could. As we are looking at this, okay, we got to here. All right, we got to here, you guys. Let me talk to you. I mean, what does this mean? Well, this is going to be, theoretically could be a negative number, but I mean, t could have been a negative number. When you square a negative number, you get a positive answer. The square root of a positive answer is going to be positive. So we're not, let's not, let me write some things, and then let me kind of like throw a few things by you if you don't mind, because I think we need it to do that. Otherwise, we get bogged down a little more than I think we need to on this stuff. So we got this. Okay, that's the absolute value of t. Theoretically, it could have been a negative number here. Yeah, I mean, I guess we could say that. There's a lot going on the other way too. How the cosine would play out as well, right? How that all plays out. The cosine has some pretty crazy behavior if you're looking at it. So you got to watch out. I mean, you got to say essentially this, but that's okay because both negative or both positive. If they're both negative, cool. If they're both positive, also cool. But let's say this. So it's not going to matter too much. And the big thing is you can multiply by -1 on each side, and you're fine. So this could have been a negative t, and this could have been a negative a times cosine of theta, whatever. The big thing is we are justified going here. We're justified going here, and this is a cosine theta. So it works. It works. Can we talk some more? Yeah, here's one thing that kind of pops to mind, I guess you could say. Try to say exactly what we were doing here. Now, for some reason, I'm trying to look at. what happens here, this right here will be, there's a number of things you can say here. Let me absolutely try to say something here on this. This guy is A cosine, so let me just try to see here what I actually had done. There's a number of ways you can do this. Once you get to here, guys, I think I kind of jumped the gun to the point where I got to like redo this a little bit, but this is fine. This is right here. We know this. We've talked about that. What is going on here? You can see there's a lot going on here in the sense that this is A cosine theta, and we can find out for some reason here. I know we're eventually going to do derivatives. Oh, this is fine. There's nothing wrong here. For some reason, I just want to see I don't want to say too much and then not say enough. At the end of the day, T times this is just the magnitude of B. Equals A cosine theta. Yeah, that's true. I guess kind of the 800-pound gorilla in the room, you guys, is basically, okay, what's T? If we can do that, we're in pretty good shape to find it. And I can't really chase my tail on this one too much, but let's see how actually we had gone about it. We had said, there's a number of ways you could have done it. Now, this is true story. Now, can I ask you another question? Is it true that A cosine theta, this is going a little separate now, guys. We've already kind of said this. We've said what we said. I mean, let's kind of leave this alone right now for a bit. And there's a number of ways you can leave it alone or not leave it alone, but let's leave it alone. A cosine theta is the same as A times B cosine theta over B. Well, I'm not saying anything too profound here, guys. AB cosine theta divided by B is A cosine theta. No big deal. Now, why are we doing that? Well, because that means that A cosine theta is indeed this, which is the same as, didn't we say that AB cosine theta, we've been kind of saying that from the very beginning, that is A vector dot B vector over B. Well, yeah, true. I'm not saying anything too profound. If I multiply by B on each side, A vector dot B vector is AB cosine theta. Yeah, true. But that's pretty significant because this A cosine theta is the same as that A cosine theta, which means in place of A cosine theta, you can put T times B, still not obvious. Okay, so what? What the heck is T, right? So there's something. So there's a whole lot here. I write it a little differently in the notes, you guys. I'm a little more formalistic in the notes that you'll see. I guess that's a horse apiece too. You know what I mean? You're looking at something like this. Well, okay, that is saying something. But what is it saying? Well, okay, so we say that's A cosine theta. I still, okay, it's true, but so what? Well, I'll tell you what. We said this. Let's take it one step further a little bit and kind of keep it in the back of our mind, I guess you could say. T is equal to A vector dot B vector. Let me divide by capital B on each side. The magnitude of B vector, I got this. Okay, what does that mean? Well, that means when we got that I just pointed out right there, T equals A vector dot B vector over the magnitude of B squared, when we have that, the distance between the point A1, A2, A3 and the line B1T, B2T, and B3T will be at its minimum possible value because it is a perpendicular distance between the point and the line when you're actually doing it. Remember what we said, guys. We got to here. We've been saying this. Well, okay, we've been saying this in one form or another all day. That's a perpendicular distance. Where does that occur? When this guy is expanded to get out to here. To get out to B1T, B2T, B3T. As far as here, and this is the other guy. So you got this, that distance right there is a perpendicular distance. You will have a perpendicular distance when that happens. Notice there's no other, you can find other distances too. This distance, that distance out there, distance that way, onto this line, go down to this line. Go down to here, go down to even through this guy if you want. This way, this way, this way. The minimum distance is right here when you find that T. What is that T? That T is equal to this. That's the T where B vector times T is equal in magnitude to A cosine theta. The magnitude of B vector times T, let's just don't worry about negatives and positives right now. We sort of knocked that out here in a backhanded way, so let's not deal with it too much right now. So let's just say everybody's positive here. If everybody's negative, that's fine too. Multiply by -1 and you're fine. You're good. Not a problem. Make sure that they're positives all to begin with. You can always throw a negative on there if you need to, but if they're negatives on each side, it holds. So this is true. You divide by, this is true. You divide by B. It's a pretty interesting format here. I mean, A cosine theta is AB cosine theta over B. That's the same as A vector dot B vector divided by B. This A cosine theta is TB. TB is A cosine theta. This is A vector dot B vector over B. That's where this became that. So I just wrote it here. This guy is just TB. Okay? And divide by B on each side, you got this. This will give you the minimum distance if you're actually looking to find the distance. Well, I'll tell you what. Maybe there's something we can do here. Let us write all the possible distances that could be from A1, A2, A3 to the line B1T, B2T, B3T. Notice this is right here a particular T, the T we're thinking about. But that T could be anything, guys, and this line could go from all the way this way, or it could go all the way this way, as much as you want. I'm just saying there's a particular T that'll bring it right here. But man, there's distances right here. There's distances right here. Well, let's look at all the possible distances. And then we'll find the minimum value of t. The minimum value of t is guaranteed to tell us what t is. That'll give us the minimum distance. The minimum distance is the perpendicular distance. We're solving for t. You're probably wondering, what are you talking about? Who cares? I already solved for t. Yeah, but I'm going to solve for t with different values. And then I'm going to really see what I can do. I'm here so far. So far, we're here. And then from here, we got to see what we can do. Okay. There's a lot there. Things you just don't want to erase. You'd like not to erase any of them, I guess. Tell you what. Let's do what I just said. Let's find the minimum value of a function. Let's find the minimum value of a distance function. So let's see this. Let's write all the possible distances, guys. All the possible distances from the tip of this vector, the tip of the A vector, which has coordinates A1, A2, A3, to the line. Well, this is the line, this is the point we want to find, but man, there's an infinite number of points, and the distances are from here to there, that's on the line. From here way over to here, that's on the line. From here way over to here, that's on the line. From here over to here, etc., etc. So let's find a formula for that. Well, I don't know. We're talking about A1, A2, A3 to the line. B1t, B2t, B3t. This to the line here, express the distance Okay, so what are we doing? Yeah, they want us to express distance from the point A1, A2, A3 to the line defined by the vector B vector, which is shown to be B1t, B2t, B3t. What is going on here? Well, I'm going to make it a distance function. I'm going to call it capital F of t. Capital F of t is the distance as a function of the parameter t. Capital F of t is the distance as a function of the parameter t regarding the distance, indeed, from the point A1, A2, A3, those coordinates, to any coordinates defined by the vector, to any coordinates on the line defined by the vector B vector. And the coordinates are basically, these are basically the coordinates of the line. The coordinates of the line, you guys, I guess you could say, in another way here, I guess you could say, is the tip of A vector is this. And maybe this is easier to look at than the AX, AY, AZ. Maybe it's a little more compact. I don't know. A vector, this point to this point. I'm going to write it as a point. It's a moving point for sure. There's an infinite amount of points here. T could be 0, which means if t is 0, it's right here. The vector's been crunched up to here. If t is a positive number, the vector expands this way. A negative number, it expands that way. But I can find all those points lie on a line determined by the vector b vector. All the points that lie on the line that are either in the same direction as b vector or completely diametrically opposite direction to b vector, they are anti-parallel to b vector, but they're all on that line determined by b vector. Where t is less than infinity, where t is any real number, I get an infinite number of points that give me the line, if I graph it, give me the line that is determined by b vector in three-dimensional space, if t can be any real number. What are we talking about? Well, we talked about it pretty well, I think. We got this and we got this, and let's just do the Pythagorean theorem and figure out what we're going to say. So you can say, guys, on this, b1t minus a1 squared. These are the x's. b2t minus a2. These are the differences in the x's squared. These are the differences in the y's squared. Do not want to erase this, but I might have to. And I'll write it down here, I guess. If I don't erase it, this is going to look kind of ridiculous, but okay, what are we doing? Well, we just did it. There it is. That's the function. I didn't write it the way I like to write it because I didn't want to erase this, but you know where I'm coming from. Okay. If that's the case, all right, guys, let me finally erase this, I guess. All right, well, here we are. So you've got that and you got that, the end of that, and you got a whole bunch of stuff going on here, guys. Wrote that down there, got that. Look at that, look at this function. It's crazy, but it's there. This is the Pythagorean theorem applied to three-dimensional space. Capital F of t will have its minimum value when what is underneath the radical has its minimum value. Look, guys, you don't need to get too crazy when you're doing this. You can if you will. You know, you can if you wish. You don't have to. I want the minimum value of capital F of t. We know the way that I have drawn this is a non-trivial scenario. This right here is b vector. This right here is a vector. This is a non-trivial scenario. They are separated from one another substantially. If they're in some substantial sense, if they are separated from one another, this is going to be a non-trivial answer. F of t is not going to be 0. But its derivative is going to be equal to 0 once you get the minimum. The minimum distance will occur when what's underneath here is a minimum. So just get the derivative of what's underneath there, and set it equal to 0. It'll have its minimum value when what is underneath there has its minimum value. So basically you could say, okay, you don't have to do that. If you want to put this big square root, call all of this here the quantity, all of this, to call all of this quantity to the 1/2 power, and then do the derivative. It's going to work just fine. It's a lengthier process than you need to do, but it'll work. The minimum occurs when the stuff driving it is going to be at a minimum. This stuff underneath is what's going to do it. But you could take the derivative of the whole thing if you want. It's a lot lengthier process. It works. It works fine. Got a better idea. Whatever's underneath, if it's at a minimum, we're in business. How about small f? How about small f of t equals b1t minus a1 squared plus b2t minus a2 squared b3t minus a3 squared. If we find the minimum of f of t, then we find the minimum distance. It's that simple. You got to remember, the whole thing is this, guys. I mean, capital F of t, ladies and gentlemen, is the square root of small f of t. So what does that mean? Well, there's a lot of things you could do here. I mean, you could say, I didn't really go there, and I don't know if you want me to go there, but you got this is equal to the square root of f of t. You got f of t is equal to small f of t, the whole thing taken to the 1/2. Yeah, that's true. If you want to go at it, I mean, I want to live, what the heck? I entered the dance, I got to dance, guys. I mean, if you go here, and I guess the symbolism makes it a little easier anyway. If you've got small f of t, the whole thing to the 1/2, if you go df of t dt, do the chain rule. You got a half of f of t to the negative a half times the derivative of f of t. Really? Yeah. What does that mean? It means a lot of stuff. Just for the sake of the mathematics, guys, so we're not really, nobody's getting cheated on this one. And that's d small f dt. Really? Yeah. It's pretty interesting matter in its own right, I guess you could say. That is what it would be if you were actually doing it. Now, if you're going to set that equal to, set something like that equal to 0, guys, I mean, that's a different dynamic. What would happen is, see, the bottom guy ain't going to be 0. We already said it's not trivial. This f of t, these guys have no, when you're squaring numbers, the answer at the end is greater than or equal to 0. You don't get negatives, first thing. Second thing, they're not located, I mean, they may, I'm just trying to argue with myself here what you could say here to make these, if you want to look at something. You can't, this thing can never, the way this is structured right here, guys, all of this can never be 0. It's always a non-zero number. If you set this thing equal to 0, this never is 0, the way we've constructed it. If it is 0, we got division by 0 and it's going to be a problem. It ain't going to be 0. It ain't going to be 0 because they don't land right on each other. When two vectors land right on each other, one's on the other, the perpendicular distance would be 0. These are not collinear vectors. They are not collinear, but they are coplanar. So you're not, the non-trivial scenario that we got here, this is never equal to 0. So if you multiply by 2ft on each side, well, yeah, I know. I already, we know. We know. We said that 10 minutes ago. But I just wanted to tell you again. I wanted you to kind of look at it. Yeah, it's coming down to here. And that's exactly what I'm going to do anyway, guys. Forgive the digression, but I think it's an important digression we got to make. Now, we already knew it. Our gut feeling was already telling us that. What does this more or less little bit of formal mathematics tell us that I just looked at with you? What does that tell us? It tells us what we already knew. If this thing on the bottom is a minimum, then the whole thing's a minimum. So if I can get the underneath function to be a minimum, I'm set. So that's what we're working with. So with that in mind, and of course I just erased what I wanted to have up there. Okay, sorry about that, guys. All right, I'll have to rewrite it a little bit, but that's all right. What's going on here? I mean, all right, we said a lot of stuff. Just write it again, guys. Let's go for it. I mean, get this thing on the road. We got this. I want to set the thing equal to 0. Well, let's take the derivative. Figure out what we're doing here, guys. Get some more chalk. Okay, so let's go. Take the derivative with respect to t. You got, let's do the sum rule. Let's do the chain rule and the sum rule. That's the first part of it. I'm just doing right here. I'm going to do this guy first, then this guy, then that guy. Let's go. Chain rule, go here, then go derivative of b1, t. That's just b1. Same thing. Same exact process. I'm sorry, that'd be a t right there, guys. Yeah, that's true. Let's keep talking. Let's set this derivative equal to 0. Set the derivative equal to 0. There's B1. Tell you what I'm going to do. Yeah, no, well, whatever. We're not going to worry about it. There's a 2 right here, a 2 right here, and a 2 right here. Let me take the 2 out of there. Let me just take the 2 all the way out of there. Let me take each one of these. B1 squared t minus A1 B1 now I pulled the 2 out of all 3 terms. Then I multiplied here, here, and here. And what we get is B2 squared t minus A2 B2. B3 squared t minus A3 B3. It looks a little more messy than it actually is. It comes out of here pretty good. Now what did we do? Well, what you're going to do is divide by 2 on each side. Okay, yeah, it's nice that it's set equal to 0. 0 divided by 2 is still 0. And we end up getting is, we got 0 equals B1 squared t minus A1 B1. We've got B2 squared t minus A2 B2 plus B3 squared t minus A3 B3. Yeah, looks pretty good to me. What's going on here? Well, I mean, I'll tell you what, there's a lot of minuses here. That's the same as plus a negative. We're not worried about that. We know how to do it. B1 squared t plus B2 squared t plus B3 squared t minus the quantity A1 B1 plus A2 B2 plus A3 B3. True. There's a lot you can do here. Why don't you take all this and get it over there. Do the algebra. A1 B1 plus A2 B2 plus A3 B3 equals all this. Well, what is all this, guys? Let's cut to the chase here. T B1 squared plus B2 squared plus B3 squared. We're not done, but we're getting there. Yeah, that's true. What's going on here? What is this? Well, we've kind of delivered this speech a number of times. The magnitude of a vector is the square root of the sum of the squares of its components. In plain English, in plain English, B vector is defined by B1 I hat plus B2 J hat plus B3 K hat. B1, B2, B3 are the magnitude of the X, Y, and Z components respectively, or at least within an absolute value away from being that. If you square B1, square B2, and square B3, you're doing the Pythagorean theorem in three-dimensional space. Square B1, square B2, square B3, add them together and get the square root of that sum, you got the magnitude of B. Another way to put it is B1 squared plus B2 squared plus B3 squared before you do a square root is the magnitude of B squared. The magnitude of B vector squared is B1 squared plus B2 squared plus B3 squared. That's pretty significant. What we're talking about is A1B1 plus A2B2. Well, guys, I need more room. I think we finally erase this thing. Probably finally erase a lot of stuff, actually. So let's do it again. A1B1, A2B2 plus A3B3 equals T B1 squared plus B2 squared plus B3 squared. Great. What does that mean? A1B1 plus A2B2 the B1 squared plus B2 squared plus B3 squared is B squared. Really? Interesting. Maybe I should have written this differently. I'll tell you what, let me write it differently now. Multiply by B squared on each side. Really? TB squared, huh? I'm not saying anything too profound, guys, when I'm saying it's the same thing. The heck does that mean? Well, it means something pretty fascinating. A vector dot B vector is A1, B1 plus A2, B2 plus A3, B3. Whoa. It almost looks made up. Oh, gee, it's so convenient looking. So convenient looking, let's make it up here. Let's put the 1s together, let's put the 2s together, let's put the 3s together and say it's equal. It's true. It works. Absolutely works. I mean, in the trivial case that the vectors are right on each other, it's just magnitude of A times magnitude of B. But still works. Still works. Now, you got to watch it a little bit, though. That's just it. But it works. It works fine. I'm trying to just argue with myself a little bit. I look at some what-if scenarios, guys, but I don't think the what-if scenarios really amount to anything. The big thing is, the trivialities are the trivialities. Anything outside of that, how that whole thing would play out. I mean, what are the distances between one point and another, projection-wise? But even here, I'm just trying to just figure out whether they would be the same. No, this is fine. This works just great, guys. And this is the same as this. And this is just the same as. Yeah, they're one and the same. What does that mean? It means just what you saw. I mean, at the end of all that, you can do it with the notation that's probably, again, I just think a little more intuitive, but since I didn't start the problem that way, I just stayed as is. But remember, that this is just the x component of A times the x, this is the x component of A times the x component of B. The y component of A times the y component of B. The z component of, the x component of A times the x component of B. The y component of A times the y component of B. The z component of A times the z component of B. Basically, guys, when we're talking about it, you can write it as the dot product. You can write it like this. Magnitude of A times the magnitude of B times the cosine of theta, and you can take care of all the formalities if the thing is standing straight up. There's like a number of ways you could do it, but t would be 0 in that case, so it would be 0. There's a number of ways you could figure a lot of this stuff out, you guys. Even in the what if scenarios, guys. I don't want to be too overly rigorous to the point I'm trying to overturn mathematics that mathematicians who knew much more than I'm ever going to know were able to develop. But the argument I show you does work. It works completely, and that's the main thing. The trivialities are themselves trivialities and can be figured out pretty easily. That's not our business right now. The big thing is the dot product of A vector and B vector is equal to AB cosine theta, and the dot product of A vector dot B vector can also be written as A sub x, B sub x, A sub y, B sub y, A sub z, B sub z. This is a lot more intuitive. I almost regret doing this. But the A's are just associated. You saw what I wrote early, what I wrote very early on in this whole discussion. A vector, capital A vector is lowercase A1 I hat plus lowercase A2 B hat plus lowercase A3 K hat. B vector, capital B vector, is lowercase B1 I hat plus lowercase B2 J hat plus lowercase B3 K hat. The A1, A2, A3, lowercase A1, A2, A3, are respectively identical to capitals a sub x, a sub y, a sub z. The lowercase values b1, b2, b3 are equal to respectively the uppercase b sub x, b sub y, b sub z. And you saw me do it when I did it earlier. This is pretty profound stuff, guys. Once you get to here, it's a whole lot. It's a whole lot. And, you know, as we look at it, I mean, when you have, you know, if the thing, what does that mean? There's a lot that it means. I mean, if you have vectors perpendicular to each other to begin with, that's A vector and that's B vector, or should I say the other way around? Not that it matters. I mean, but this is B vector and that's A vector. The minimum distance to this point were if t were equal to 0. Well, if t is equal to 0, those are equal to 0 as well. If t, if t is equal to 0, these would also have to be equal to 0. And, I suppose that would make a lot of sense in that regard. Pretty fascinating stuff. If one's on the other, b hat, and the other one goes all the way across here, and that's a hat. For that minimum, where would it be? Where would it be located? It'd have to be somewhere over here. There would be some kind of a t associated with it to get us there, and it's coming out to here. There's all this, because when we did this, when we first did the problem, you guys, we didn't really concern ourselves with specific locations. Hopefully I made it a little easier to look at when, how this is going to play out. But literally, we never specified. And we really weren't worried. I mean, I guess it would have been a big problem when you were getting the square root of something. That's got to be a minimum. Well, the minimum value's got to be 0. So I think we would have been okay. I mean, we could have found it in such a way to have gotten ourselves there. We're not any kind of an issue, guys. Not to worry about it. But this is pretty crazy stuff. How it plays out and how the components all play out. Very important. Okay. I guess we did it in very. I'm just trying to justify this as well to myself. I guess we did it with. We didn't really specify what a sub x, a sub y, a sub z were, and we just said generally they're out there, and when you're going to do it, when you're looking at, and again, now I regret having erased some of the stuff, but there was no room for it, guys. When you're doing the square root of all that, is there a minimum distance? I guess you could say. So I think the way it's set up, I think the mathematics is strong. It'll hold just fine, even in the special case scenarios. We can get out of there pretty good. Okay, if we look at it. Very confident about that. So, because when you have, you did the whole thing here, and you actually said that, we said df dt, this is really the rigorous way to do it, to square root of, I think when we actually had done that, we'd said, right. Let me just for the heck of it, guys. I mean, let me try to leave this alone, though. It's a very important conclusion, and that's going to drive a lot of what we're doing. Just look at some special cases here to make sure we're not getting into any kind of trouble here, guys. This is what it is. The only thing that's kind of scaring me is division by 0, but I don't think that's something we need to be worried about. If it were the case, we can get around it by just keeping the small f of t. But if we said that capital F of t is equal to the square root of this, and then you do the derivative, just to be rigorous here, guys, just to give some kind of foundation. I mean, there is a lot of foundation to this already, guys, obviously, I believe, but let's see here, when you actually do this, you're getting the derivative of f of t, the whole thing taken to the 1/2 with respect to t. At the end of the song and dance, it comes out to this square root of f of t I mean, there are scenarios where this could be an issue. I'm just saying them now. I mean, if A vector and B vector are the exact same magnitude and they lie on one another, I mean, that's a bit of a, obviously it's kind of a trivial point, but not really a trivial point. If they are equal magnitude and they are collinear, the distance between them is 0, and then this becomes some kind of an issue at that point. At that point, perhaps the L'Hopital's rule could be something that could be done. But so I think a better way to go on that. Otherwise, it's not really. That's the only time you can be having some kind of an issue regarding that. Let me just see what else. It really, and you set all this equal to 0. Sure, it can work. We can figure it out. Where that plays out, you guys, I'm still just trying to think a little bit about where you would go with that. That is f of t itself. See, the square root of f of t on the bottom would be capital F of t, regarding where it could be. There's ways around it, guys. I think if you stay right here, there's more than enough foundation to get you there. You can get away from the special case scenarios that could mess it up. This generally holds. It definitely is going to generally hold. This right here is going to be f of t. To do it, you'd have to have d. There's a whole bunch here. What you could say, df of t dt equals 2 times, and that is the big function. And then, the square root of small f of t is this. So, if you go that way, this could theoretically be 0 distance between them, and that would be 0, and it would still hold out. I think very, very best way to do it is there a minimum distance? If there's a minimum distance, whatever is underneath the radical, when you take the derivative of anything that's underneath the radical, you'll take the derivative of anything that's underneath the radical and set it equal to 0. That's more than enough to get the minimum. So I think we're fine. So pretty important stuff, very, very fascinating stuff. What's going on here? Well, we looked at it, we proved it. Are there certain conclusions that can be drawn associated with it? Well, yeah, I mean, in those, among the conclusions that can be drawn is there some kind of commutivity here? Is there the associative principle? Is there the distributive principle? Is there the distributive principle done in a multitude of ways here, guys, where this stuff can actually arise when we're doing this? So I think what we can say, guys, I'm running out of chalk. Look at it. Look at it good. What does this mean? Well, I think rather obviously it means this. I mean, A vector dot B vector. Let me use the A sub x's, A sub y's, A sub z's The b sub x is b sub y is b sub z's. We said it's equal to this. A sub x, b sub x, a sub y, b sub y, a sub z, b sub z. Yeah. In all scenarios. I mean, we said we can get around the trivial scenarios that could probably create problems for us. We can get around it by just talking about what's underneath the radical, getting the derivative of what was underneath the radical. Get the derivative of what was underneath the radical and then mess with it there. You should be okay. So we got to here. We said this. Yeah, we've said this. Does that mean if you do this, yeah, that's what it means. Since these quantities are not necessarily, I mean, there's an argument here. Again, one of these other arguments you could make, I guess. They're not really specific. It doesn't matter which one you could be finding the projection of a vector onto b vector, or you could be finding the projection of b vector onto a vector. Projection of a vector onto b vector, or the projection of b vector onto a vector. Either way, not really an issue. These are identical. Why is that? Because here, by the commutative property, these two scalars, if you reverse the order of the multiplication, doesn't change what the quantity is. Same thing here, same thing here. So is there a conclusion to be drawn? Yeah, there's a bunch of conclusions to be drawn. A vector dot b vector equals b vector dot a vector. True. Got some more questions to ask. You could say a vector dot the quantity b vector plus c vector. Is there some kind of distributive property here that could work? I don't know. Let's ask. This right here, let's see how we want to talk about it, I guess you could say. This right here is a vector. Well, let's do this. Let me kind of jump to it, and you know, I wish this was live, guys. We could talk. You know, we get feedback from one another. I guess it's always a big challenge in this stuff. But let's have a look at it. I tell you what. Don't we know that generally speaking, a vector dot b vector is ax bx plus ay by plus az bz. What does that mean? It means you take a vector's x component and multiply it with b vector's x component. And you add that product to the product of a vector's y component multiplied with b vector's y component. And then you add a third product to the other two products that were added together. You add the product of A's z vector, you add the product of A's z component multiplied with B's z component. Okay, that's what I just said over there. It's a little easier over there than me trying to say it, right? Well, what this is right here is, this is AX multiplied with, let's be careful here. There's a lot of ways you can do this. B vector plus C vector, the x component of the sum. plus AY times B vector plus C vector, the Y component of the sum, plus AZ, which is B vector plus C vector, their Z component. These are scalars. They got to be scalars, guys. You say, oh, if they're scalars, Malus, why are you writing down B vectors? Why are you writing down vectors? Well, I'm saying here's my shorthand. I don't know if it's a good shorthand. Maybe I'll show you another one in a second that might be better. A sub x, the x component of A vector, times the x component of the sum of those two vectors, plus the y component of A vector times the y component of the sum of those two vectors. The z component of A vector times the z component of the sum of those two vectors. What's going on here? Well, can I ask you a question? Is it true, maybe this is easier, I don't know how comfortable you are with that. Let me say something else that maybe make you more comfortable. Is B vector plus C vector going to be AX, AXI plus AY J plus AZK plus C sub X I hat plus C sub Y J hat plus C sub Z K hat. Yeah, that's true. It's true if I get the letters right. I'm sorry, guys. I mean, the argument's right. The letters are wrong. Okay, my mistake. Okay, that's right. Now that's right. Okay? What does that mean? B vector plus C vector. I'll tell you what, just to add the components together. Bx plus Cx, that's an I hat. By plus Cy, that's a J hat times all that. And Bz plus Cz, that's a K hat times all that. This guy right here, Bx plus Cx, and this guy right here, By plus Cy, and Bz plus Cz are what I meant by those up there. So I don't know. I'm not crazy about my notation here, but in fact, I'm not crazy about it big time to the point where I'm going to say something else. I mean, let's in place of those, but I just told you what they are. Awkward as it may be, the way the notation was that I constructed it. Let's say this. The x component of this guy is Bx Cx in terms of magnitude. And remember, the dot product, ladies and gentlemen, is a vector. Scalar times scalar, scalar times scalar, scalar times scalar. Add the scalars together and you're there. This guy right here. Didn't we say this is the J, this is the I vector, this is the J vector, this is the K vector. Stuff sometimes easier said than done, I guess, right? But there it is. Yeah, true. True. That's true. Why don't you distribute the A? Distribute the AX to these two guys. AX, BX. Starts to look familiar. AX, CX. AY, BY. AY, CY. AZ, AZBZ, AZCZ. What is going on here? Yeah, you're looking at it. If you think something looks like it should, AXBX, AYBY, AZBZ, AXCX, AYCY, AZCZ. Yeah, you're seeing it right. What we have here in this whole process is, let me see here. I don't, like I said, we got it. Eventually, I'm going to even erase that eventually, I think. A vector dot B vector, A vector dot the sum of A vector dot the sum of B vector plus C vector is equal to and again, I don't want to keep beating this thing up, guys, but don't worry about it. Even in the cases where there's trivialities and there's maybe a contradiction coming up, we can work through it with the mathematics. This is a valid conclusion. When they said A vector dot B vector is A sub x, B sub x plus B sub y, I'm sorry, forgive me. When they say A vector dot B vector is A sub x, B sub x plus A sub y, B sub y, plus A sub z, B sub z, it universally holds. There's ways that you can make the mathematics work. That's not an issue. So don't lose any, so we're fine. I mean, we have full confidence in that. This stuff is used throughout in so many things, in so much of the mathematics and physics. Beautiful stuff. What's in the yellow, you guys? What's going on here? What's in the yellow? What's in the green? What are we talking about? B vector plus C vector. At the end of that song and dance, what happened? Well, yeah, I know, but what is this? This is A vector dot B vector. What is this? This is A vector dot C vector. A vector dot B vector. Okay, hold on here. Yeah, right. Let me write it. Let me just write it out, guys. True. We looked at it, we got it. Yeah, look at it. I mean, it's looking pretty good. What we had is, at the end of all that, it came out to here. So let me kind of write it here. I'm a little apprehensive, guys. Forgive me for checking everything here, but I'm always how good the camera's going to pick up on everything. So, yeah, so there you go. You saw the argument. Pretty straightforward stuff. Tedious, but straightforward, I guess you could say. obviously, guys, if you were ABC, hey, why don't you throw a D vector on here just for fun? Yeah, I haven't had this much fun. Haven't had this much fun since I fell out of a tree, I guess. I don't know, whatever, how fun that is, but put another vector on there. What happens? What's going to happen when you do that whole thing, you guys, is essentially, I wish I wrote this. If you're going to put a D vector on there, you know where this is going. I'm going to take this. Let me see what I can do without erasing everything. I think I don't think there's any way around it. I'm going to have to erase a lot of stuff, guys. But that's all right. The way the argument plays out, there's some pretty important conclusions we can draw. I mean, I'll tell you that for sure. Okay, if you were going to go with the D vector there, guys, well, since I erased so much, I mean, what else? Well, what does that mean? Well, it means A vector dot B vector plus C vector plus D vector means the x components are all added together. That's an I hat. The y components are all added together. And the z components yeah, that's crazy. Yeah, you know, what did we say? I mean, the general look on this, guys, that we got, we said, you know, a lot of stuff here and how this plays out. So, again, we said A vector dot B vector is AB cosine theta, and A vector dot B vector is AX BX plus AY BY plus AZ BZ. Sorry, guys, I always hate going to the edges like this, how it goes. And the more, guys, again, the more I look at how we did that derivative, dealing with the thing underneath the radical was the best way to go, because it got us out of all the trouble of dividing by zero, and we got valid results. We got this. So we're doing great. I don't know how clearly written that is for you. The visibility varies where you are on the board, you guys, but it's a great setup, and I got a great coworker who's made this possible for me, guys. Otherwise, I don't know, wouldn't be able to do any of this, actually. He's done some great work. All right, so we got this. You know this is how it plays out, you guys. Since that's the way it plays out, what's going to happen here? Well, that's the A vector is the same as AXI plus AYJ plus AZK. Go eyes with eyes, go i's with i's. J's with J's. And Z's sorry guys, old injuries. Not moving too good. Here we go. It's looking good to me. The white, the yellow, the white, the yellow, the green, the white, the yellow, the green. Look. The I hat goes with the other I hat. The J hat goes with the other J hat. The K hat goes with the other K hat. At the end of the day, you got this. AX, BX plus CX plus DX, AY, BY plus CY plus DY, AZ, plus BZ plus CZ plus DZ. You guys know where I'm going. If you take the AX and link it with the BX, then link it with the CX, then link it with the DX. If you take the AY, link it with the BY, the CY, the DY, the AZ with the BZ, the CZ, the DZ, man, at the end of the day, guys, you can, and there's different proofs here on this. At the end of the day, you're just getting this. This whole process here, this whole thing right here, is going to be, well, let's just do it. AX, it's going to be, you're going to have AX BX plus AX CX plus AX DX. You'll see what I'm doing in a second here. Then you're going to have, that's it. You're done with that. Then you're going to have AY BY, AY CY, and AY DY. Then you're going to have AZ BZ with what's going on here, AZ CZ, and AZ DZ. They're all added. Well, if they're added, it doesn't matter what order you're adding them in. So I'll tell you what, ladies and gentlemen, I'm going to do this. I'm going to do this. Then I'm going to do this. It doesn't matter the order. They're all getting added. What's going on here, guys? Look, this is AXBX. This is up here, up top, AXBX plus AYBY plus AZBZ. This is AXCX, AYCY, AZCZ. This is AXDX, AYDY, AZDZ, which is A vector dot B vector plus A vector dot C vector plus A vector dot D vector. A vector dot B vector plus C vector plus D vector equals A vector dot B vector plus A vector dot C vector plus A vector dot D vector. By induction, you can keep putting another vector into the mix. Any number of vectors into the mix you can put. And by induction, you can show that it works. We show that it worked here. You could have, and they show in this book by the authors, a calculus book, great calculus book, in 1984, Munham and Foulis. Munham and Foulis were the authors, 1984, for the calculus book. They tell us a pretty fascinating proof on that. You could have taken this guy, and since you already proved this guy, since you already proved this, you prove that's true. Since you prove that's true, tacking on another vector here, you could treat this as a single vector and then tack on this guy. So which means it comes out to this right here, we already said it would come out to the dot product of B vector plus C vector. That's the equivalent of a B vector. This whole thing's like a new B vector, a B prime vector or something. This guy plus A vector dot D vector. And we already knew that came out to A vector dot B vector plus A vector dot C vector. And this guy. So you could treat this as one of the vectors. A new B vector, and this is a new B vector, and this is D vector. There's only two vectors here. What do you mean? There's three vectors. Yeah, when I add them together, it's one vector. One vector and another vector. When I add two vectors together, distribution occurs. Well, here, distributed here, you got that. And then, here's two vectors. Here's just two vectors. The sum of these is one vector. Here it is, the dot product of this plus the dot product of that. Yeah, well, that was, you break it into this, so three of them are going to happen. So what happens is this, A vector dot B vector plus A vector dot C vector plus A vector dot D vector. Well, you can do this by induction. You can put any amount of those that you want, and it works. Any amount of those that you want on there, and it works when you do it. So the distributive property works from the left-hand side moving toward the right. If you put a single vector, so to speak, by itself, and it's as simple as that, you guys. That's great. That's true. Say something else. Well, can we say something? Yeah, it works if you're moving a single vector from the left and doing a dot product with the sum of vectors, you get what you get. Absolutely. Now, Munham and Foulis were brilliant how they did this. That last thing I just showed you was, again, the calculus book from 1984, Munham and Foulis. That thing I showed right now, that's how they kind of went about it. And they talked about that's by induction. That's by induction. Does it work the other way, and can we expand it further? Well, let's say it. Let's just say a couple things here. Now we said it, and then we'll just summarize it at the end, and we'll leave it until we go to the cross product. Cross product's got a lot of ways to look at it. We'll cross that. We'll bring everything together, guys, at the end, and I'll have the documentation for you in case you would like to see it. Okay, so yeah, we said it works if you got a single vector on the left-hand side. What if you have a bunch of vectors? You got a single vector on the left-hand side and you bring it into other vectors, a multitude of vectors on the right-hand side. A single vector, a single vector on the left-hand side, so to speak, and you do a dot product with a multitude of vectors on the right-hand side. Well, you saw that it works. We saw the distribution works in that regard. I think I'm going to go to Munim and Foulis again. I think they did something similar to this when they were doing this. Let me just give me a second, guys. Here, make sure this is okay. Got to make sure the audio quality is okay. All right. So what? Well, there's a number of ways you can go here, actually. Here's one way. It's pretty quick. I think this is Munim and Foulis again talking about this, and I'm sure other mathematicians have talked about it as well. A vector dot B vector is the same as B vector dot A vector. Fair enough? Yeah, we've said that. We've said that. A vector dot B vector is equal to B vector dot A vector. Okay. So what does that mean? That means this. You got to remember, when you add these, you get one vector. This whole thing about one vector is overrated, guys. And that's good that it's overrated because it makes our job easy. If you add a multitude of vectors together, you get one vector. Their components all add up together for one new x component. All their x components add up together for one x to make you the addition of all the addition of all the x components together give you one big x component made up of the addition of all the x components. Add all the x components together and multiply by I vector, you got your new vector. You got the start of your new vector. Do that with all the y components and with all the z components, multiplying by j vector and k vector respectively, you got a new single vector made up of all the components, all the respective components. So it's overrated. Don't be losing a lot of sleep on that. Yeah, commutative property holds. Yeah, absolutely it holds. We talked about that. Okay, good. That's good because we determined this. This is Munim and Foulis again, guys. I'm going on memory now from what they had done, but they wrote a great textbook. Great textbook. Yeah, that's true. What does that mean? Yeah, that means this is true too. That means it's the same thing here. Yeah, it is the same thing. Is there a way we can be kind of slick about it? Maybe you see where I'm going, guys. We just said the dot product was commutative. Why don't you do this, please? We just said the dot product was commutative. Darn right. Darn right. What does that mean? Careful. It means B vector comes over to A vector and you dot it. It means C vector comes over to A vector and you dot it. Let's say that again. It means B vector comes over to A vector, B vector comes over to A vector, and you dot it. B vector comes over to A vector, you got B vector dot A vector. C vector comes over to A vector, you got C vector dot A vector. Yeah, it works. If you want to drive yourself a little crazy, you could take, well, you know where I'm going. Bx, by, bz, plus cx, cy, cz. Fantastic. Yeah, you know where it's going. You know where it's going. Bx plus Cx I hat Cy By plus Cy j hat Bz plus Cz k hat. Here's your one vector, guys. This is one component composed of the sum of components. This is another one component. This is another one component. Do the dot product as you know how to do the dot product. What's going to end up happening is you get Bx Cx times the Ax. By Cy times the Ay. Bz plus Cz times the Az. The rest is mathematics. You do the... Wait a minute. This is Bx. This is... Let's do it. Bx Ax. By Ay. Bz Az. That's that. I'm just doing it in different order, but they're all there. They're all accounted for. Cx Ax. Cy Ay. Cz Az. That's C vector dot A vector. By induction, you could play the game that way. You could go by induction and still prove it that way. This is easier, though. When it's already, you just, bam, reverse them and say it's got to be the same thing. Well, if it's the same thing, let me reverse these guys, and wow, it's coming just from there. And then just like I could make this guy as big as I want. What do you mean? Well, I mean B vector plus C vector plus C1 vector. I'm running out of letters, let's say. Let's say I ran out of letters. B vector plus C vector plus C1 vector plus C2 vector plus C3 vector plus C4 vector plus C5 vector plus C100 vector. I've got 102 vectors here. B vector, C vector, and then C1 vector plus C2 vector plus C3 vector all the way to C100 vector. Wow, 102 vectors. Yeah, I could have 1,000,002 vectors there if I wanted. By induction, this worked for any number of vectors, and if you reverse it, and you do, the commutative property tells it that'll work too. Or you could also go by induction. So it works that way too. There's different ways to do it. I show in my documents. I try to show you. I think you'll see where it's coming from. It's the same kind of argument, essentially. What's going on there? That's it. You guys see where we're going? Okay, not too bad. Now what's up? What else could we kind of do here to kind of make things interesting, I guess, so to speak? Well, we just said a lot of stuff. Let's write down what we said at least. All right, guys, we've said a lot of stuff. We've concluded some things. Good conclusions here. Good looks at what's happening here. Almost there for this part of the discussion, you guys. what happened here? I mean, what have we said? I mean, said a number of things. I mean, we've said A vector dot B vector. Now we did all these. We got all these, you guys. We said A vector dot B vector. So we got the bread and butter was this, man. It took the long song and dance to get it, but we know how to do it. It took the long song and dance to do it, but we know how to do it, guys. We're looking good. We got this, and we got that. They're equal to each other. And then we say A vector dot B vector is the same as B vector. A vector dot B vector is the same as B vector dot A vector. We also said that if you take A vector dot a whole bunch of vectors, how many? As many as you want. Let's take n of them. How many is n? Could be 1,000,000 if you want. That's equal to A vector dot B1 vector plus dot 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 A vector dot Bn vector. And we also said, and I'll organize these guys. I also said if we do a lot of stuff here if you want. We also said if you had on the other side of this thing, that's equal to B1 vector, A vector. Whoa, what am I doing? Yeah, right. Sorry. B1 vector, A vector, plus dot, dot, dot. And again, we just discussed it. You know where I'm coming from. So this is interesting. I'll try not to erase these guys. I think I've written these down on different occasions here. Let's try not to. All right. I guess the last thing you can say on this one. I mean, there's a lot you can say, guys. I'm probably what I'm trying to do here. This is kind of the main stuff. There's a lot you can say here. Neat stuff. What can we do at least for now and be done with it and kind of move on for the dot product and use some stuff to get there? Use a lot of what we've done here. We're going to do a lot of what we did here. We're going to use the reality. I'll say some things before we're done here today. Okay, you're looking at that. I guess there's a great question that comes to mind, I guess. A1 vector plus dot, dot, dot plus A sub m vector. What's m? It's any number you want. It's any natural number that you want. From 1 all the way to infinity. I mean, if it's 1, you're not going to have, if 1 is just this guy, it's A1. It's just A1. But any natural number, m. Dot. That's one big vector, guys. Don't let it scare you. We've been there. B sub n. B sub n. This is m. This is m. This is m and this is n, and they could be the same number, and they could be different numbers. Doesn't matter. So I'm trying to go real general here. I'm basically doing this. But there's going to be m times n dot products. There are n of these, one of those, n dot products. N of these, one of those, n dot products. Each one of these is going to hit that one. Wow, we got to be careful. How does this work? I'll tell you what we're going to do. We're going to remember everything we did is what we're going to do, and then we're in good shape. Then we're not going to have any problems. Okay? All right, guys, give me 1 second here. I want to make sure there's no problem with the audio. Okay, so far so good. All right. What is going on here? I tell you, yeah, I guess there's a whole lot you can do here. I guess we can say a bunch of things. It doesn't really matter which one because it's going to work. I'll tell you what I'm going to do. I'm going to take this guy, one big vector, one vector by itself, dotted with this sum of all these vectors, which is also one big vector. They're all just one big vector times one big vector. It's all one big vector dotted with one big vector. Not times, dot product, right? One big vector dotted with one big vector. It's all right. It's the same stuff we've been doing forever. Tell you what, I'm going to call this guy one vector by itself, and it's going to distribute throughout and get all those. What's going to happen is, this is one big vector, ladies and gentlemen. Call it one big vector. Okay, this is like a new vector A. This guy, A1 vector plus dot, 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 plus A sub m vector. All these vectors added together. A sub 1 vector added with A sub 2 vector, added with A sub 3 vector, added all the way to A sub m vector. The sum of all these vectors is one big vector. We'll call it A, the A vector. Oh, really? A vector, huh? You were here, and you go here, then there, then there, then there. You know the deal. B1 plus, I mean, I don't know. You want, let me just do it like this. Hopefully this is going to be okay for you guys. Yeah, that's one row, ladies and gentlemen. That's one row. Or that's one column, I guess you could say. I guess you say it's one column. Yeah, I did it with A sub 1 vector, and I combined it with n different vectors. It could be the same vector, whatever. Let's not, again, I was trying to say that earlier. Let's not get too obsessed with the formalities of it. Let's just get it done. I'm combining the A1 vector in dot product form. I'm sorry, I'm combining this entire huge vector, this one huge vector composed of these m vectors together. I'm hitting this guy n times. Correct. Guys, do you remember that it said, now let's go to this guy. We just worked with him right now. We just worked over here by my right hand. Go to my left hand now, guys. Take this guy and bring him over. Each one of these, the B1 to Bn, this is like the B1s, but now there's m of them. But each one of these is going to distribute over. What does that mean? Well, that means you're going to get this. You're going to get m of these, and it's going to be A1 vector dot B1 vector plus dot 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 plus A sub m vector dot B sub 1 vector, right? Okay. You realize you got m vector, you got m dot products, and you're going to do it n times. What's m what's m times n? It's m times n. There's m dot products, and that's going to occur n times. M times n is going to be m times n dot products. Dot bn vector plus dot plus this. Look, guys, the A1 vector, let me try to think here. Right, that should have been a vector, forgive me. A1 vector dot B1 vector, A2 vector dot B1 vector, A3 vector dot B1 vector, AM vector dot B1 vector. A1 vector dot Bn vector, A2 vector dot Bn vector, A3 vector dot Bn vector, A4 vector dot Bn vector, eventually Am vector dot Bn vector. M times n terms. How did it play out? It played out with doing the dot product. I mean, hey man, if you ask me, it's easier just go component, hey man, let me just get all the components together and get the x. Let me get, of all these m vectors, let's add all m components that are x components and get one big x component. Let's add all m components that are y components and get a big y component. Let's add all m components that are z components and get one big z component, etc. And do the same thing here. Then do a dot product. But that's what this equals anyway. That's what this equals anyway. And it distributes just like that. Okay. That's it, guys. I mean, we're gonna move soon. We'll do it when we do it. I mean, I'll come back. We'll come back and do this together. We're gonna move to the cross product, and exactly how we're gonna do it, we'll figure it out. How we're gonna do it. Should be pretty smooth stuff for us to do. The cross product is different. The dot product of two vectors was the magnitude of one vector times the magnitude of the other vector times the cosine of the angle between them. And it's got some really useful applications. So the dot product of two vectors is the magnitude of one vector times the magnitude of the other vector times the cosine of the angle between them. And that's the same as saying the dot product of the two vectors, a vector dot b vector, is axbx plus ayby plus azbz. It's the same thing as that. It's a pretty profound conclusion. Doesn't look like it would be that conclusion. They're both scalars, and it works. It works. It works. And then we talked about various identities associated with the dot product. Commutivity. I didn't do the associative property, but the associative property follows pretty easily. Once you're at, guys, all of these believe it or not, all of these are tedious once you've got the basic formulas under control and you've proved them and you believe them. Once you got them under control, you guys, the other stuff is relatively easy, but almost always tedious, as you can see. But relatively easy concept beyond that, just the manipulations, but it is tedious. Not difficult in the conceptual sense, but quite tedious, okay? Associative property holds for the dot product. Pretty obviously, when you look at the books on that, it's pretty obvious that the associative property definitely holds. Commutivity was the one that we really dealt with, and really, commutivity and the distributive property. The commutative property holds, the distributive property holds with a single vector on its own on the left coming over to the right, and the distributive property holds when the single vector is on the right and there's a multitude of vectors coming over from the left. And you know what? It doesn't matter from where they're coming over. If there's a multitude of vectors in both places, there you go. There is the distributive property, and it's strong. The distributive property holds completely. The distributive property holds completely, and the commutative property holds completely. Okay. When we get to the cross product, we'll talk about the cross product. The dot product is a scalar answer. A scalar quantity is what the dot product is. The cross product is a vector quantity, and a very fascinating conclusion. Very useful in physics as well. All right, guys. Thank you so much for your time. Take care. Bye now.